Hey everyone, welcome back to Real Analysis 1. This will be lecture 5 of the course. And in this section we're going to continue talking about sequences, but we're going to tackle some of the familiar limit theorems that you will have seen if you've taken calculus, which I'm sure you have if you're watching this lecture. So let's go ahead and jump into it. We're going to call this section 2.2 just limit theorems. Okay, and we'll tackle a bunch of these in this session. We'll state a bunch. We'll prove a handful of them, not all of them. But really the kind of the key idea here is that you've seen a lot of these limit theorems before, but you may not have seen them. You may not have seen the proof of them. And so we're going to restate a bunch of them, and then we're going to prove a handful of them. Okay, so let's go ahead and get started, and we'll just start with a nice theorem that you will have seen before. Okay, so we'll say if a sub n and b sub n are convergent sequences, right? These are convergent sequences. Well, if they're convergent sequences of real numbers, and with the limit as n goes to infinity of a sub n equal to a, and the limit as n goes to infinity of b sub n equal to b, then we'll have three parts here. So the first one is that the limit of the sum a sub n plus b sub n is just the sum of the limits a plus b. Okay, and you can probably guess what the other two will be, right? The limit of the product is the product of the limits, right? And then the quotient also, right? So if I have the limit as n goes to infinity of a sub n, so we'll say b sub n over a sub n, that's going to be equal to b over a, provided that a is non-zero and when a sub n is non-zero for all n, right? So this is a very familiar theorem. I'm sure you will recall this from Calc 1. When we first start talking about limits in Calculus 1, we definitely state this. So let's go ahead and prove, we'll prove part 2 here. The other ones will be similar in character. Obviously the details will vary, but we'll prove item 2 just to kind of show the method, so you can get used to the idea of how these types of things can be shown. So we'll begin. This is going to be mostly an algebra trick, so we'll begin with this, right? So again, we're trying to show that the product of a sub n, b sub n as n goes to infinity is equal to the product ab. So we'll begin with just what we would assume if we were doing an epsilon delta proof, a sub n, b sub n minus the limit ab, okay, that at absolute value, so the distance between those two. Okay, and we're going to just expand this. We're going to add and subtract a term here. And so what we're going to do is we're going to say a sub n, b sub n minus a and b plus a and b, right? So here's a very familiar algebra trick of adding and subtracting the same term. You just want to introduce a little more opportunity into the expression, right? And then we can break this thing up, and we'll write a sub n, b sub n minus a sub n, b, and then plus a sub n, b minus ab, right? We get a nice bit of factorization that we can do here, right? So this will be less than or equal to, we'll factor the a sub n out, okay, and we're left with b sub n minus b. And then over here we're going to factor the b out, and we're left with a sub n minus a. Okay, now a sub n converges, okay, right? We know that a sub n goes to a, right, by assumption. Right, that's part of the theorem. A sub n has a limit. The limit is a. So a sub n, the sequence converges, and so that implies that the sequence is bounded. So a sub n is bounded, and that means there's going to exist some m, right? We can say m is some integer, positive integer. So there exists an m such that a sub n is less than or equal to m for the entirety of the sequence, for all n. Okay? All right, that's just a consequence of the sequence converging, right? That just means there's some positive number that's larger than every term of the sequence. Okay, so then, right, given that, we know that a sub n, b sub n minus ab, that's less than or equal to, well, we just saw this up above, but I'm going to restate it just so we can follow the thread here. Right, now we've established that there's some m for which this is smaller. Okay, and so I'm going to say less than or equal to some m, whatever that happens to be. Toss that in there. Okay, so we've got this. All right, let's get another sheet of paper going here. And so so we've got the expression right now. We've got the expression into the form where we can begin talking about the epsilon piece of these proofs. So let's go ahead and let epsilon greater than 0 be given, right? So here we're talking about a limit proof. So someone hands you an epsilon. Now you have to show that the sequence will be within epsilon of the limit after you go out a certain number of terms. Okay, so we'll let epsilon greater than 0 be given. Then since a sub n approaches a, right, by assumption, there exists n1 natural number such that a sub n minus a, right, the distance between the nth term of the sequence and the limit a, is less than epsilon over 2 times the absolute value of b. Okay, and this is going to be true for all n greater than or equal to n1, right? And this is just given just based on the fact that a sub n converges to a, we know that this is true. Now you may be asking yourself, what is the value of expressing it like this? Well, we'll see in a moment, right? We'll see in a moment how all the kind of the arithmetic comes together. Okay, so since a sub n converges to a, we have that there exists some natural number such that once I'm past that in the sequence, then the distance between the terms of the sequence beyond n1 and the limit point are less than whatever this expression is. And the same thing is really true of the bn sequence as well. So since b sub n approaches b, there's going to exist n2 natural number, right, such that b sub n minus b is less than epsilon over 2, and here I'm going to toss in the m, right? The m is remember, that's the constant term from above. And this is going to be true for all n greater than or equal to n2, right? Now, we use n1 and n2 just because these are different sequences, so the natural number that applies to the a sub n series may not be the same as the natural number that applies to the b sub n sequence, right? So just a different notation because they're potentially different numbers. Okay. So then, right, so here's where it all kind of comes together nicely. Then, if n is greater than or equal to the maximum of n1 and n2, right? Now, what does that mean? Well, it means that both criteria are being hit on, right? So we need to basically get out far enough in the sequence so that both of these epsilon restrictions are met. Right, so if we're equal to the maximum, and maybe the maximum is n1, then that means we're also beyond n2, right? We're beyond both of them. Okay, so we're far enough out in the sequence that both of the criteria that we just stipulated above are met. So if n is greater than or equal to the maximum of these two numbers, then a sub n, b sub n minus ab absolute value, we know that's less than or equal to this constant m times the absolute value of bn minus b plus the absolute value of b times the absolute value of an minus a, right? And we know, because we're beyond n1 and we're beyond n2, that specifically this piece here is less than m times epsilon over 2 times m, and this one here is less than epsilon over 2 times the absolute value of b, right? And then of course this all works out nicely, and we see that it's equal to epsilon, right? So that means the nth term of the product is within epsilon of the value a times b, right? And so a sub n b sub n minus ab is less than epsilon whenever n is greater than or equal to the maximum of n1 and 2. Okay, right? And obviously that is going to imply, therefore, and I don't probably have to say it, but that the limit as n goes to infinity of an bn equals ab. Okay, so that's how you would prove part 2. Now, part 1 and part 3, they vary somewhat, right? But it's this same kind of idea, right? You know that both sequences converge, and so you can use that fact to show that when you combine the sequences in such a way, either through addition or through division or through multiplication, in this case, you can get to the result. Okay, very good. Let's talk about a corollary. And I think this is truly a corollary. So if a sub n is a convergent sequence, okay, and with, we'll say a sub n, the limit being a, okay, then for any c in R, any real valued constant c, we have that, first of all, a sub n plus c, the limit of that as n goes to infinity is a plus c. And second of all, c times a sub n converges to c times a. So we've definitely seen this in the past. This would have been a theorem that you saw in Calc 1 as well. And how does the proof go for this? Well, it follows directly from the proof of the previous theorem. So let's think about like the second part here, because that's gonna basically, what we want to do here is, in the previous theorem we had like b sub n times a sub n, or a sub n times b sub n, right? And we know that the limit of a sub n is a, and by assumption, and the limit of b sub n was b in the previous theorem. Well, here all we're doing is, instead of b sub n being an interesting sequence, b sub n is just a constant sequence, c, right? And so if you swap in a constant sequence for b sub n, then it's the same theorem essentially, right? And certainly the limit of a constant sequence is the constant, right? The constant value. So it's, you can see this is both this follows from 1 and this follows from 2 from the previous theorem almost immediately, if you just think of the sequence, the b sequence, as being a constant sequence. Very good. Let's take a look at another theorem. Okay, so far we've seen nothing really new in the theorem department, but we have kind of rigorously proven a theorem that we saw earlier in Calculus 1. So for this one, let's let a sub n and b sub n b sequences. And when I say b sequences, I mean b sequences of real numbers. I'll write it in this case. I haven't been writing that, but that's what that means. Now, if b sub n is bounded, so if b sub n is bounded, and the limit as n goes to infinity of a sub n is equal to 0, then the limit as n goes to infinity of a sub n b sub n is equal to 0. Okay, and so notice here that the b sequence, the b sub n sequence, we don't assume that it converges, right? All we're assuming of b is that it's bounded, right? So it may not converge, but when you multiply it term by term with a sequence that does converge to 0, all right, we get that the product converges to 0. So important to note, right? It's the whole point of the theorem. Notice b sub n does not necessarily converge, right? It's obviously this is true if it does converge, but it doesn't have to converge. So b sub n does not necessarily converge, but it is bounded. But it is bounded. Now, this is not necessarily true if b sub n isn't bounded, right? So in that case, this would fail, right? But if b is bounded and a converges to 0, then the product converges to 0, right? So if we multiply a sub n, b sub n, term by term, a sub 1 times b sub 1, a sub 2 times b sub 2, then the fact that b sub n doesn't grow without bound means that eventually this sequence will head to 0. Okay, all right, so a nice little theorem, and I don't think we'll prove it. But you can imagine, right? So the one of the keys here is that, you know, b sub n must be bounded, and to kind of see that this doesn't work for any pair of series, let's do an example. So let's consider the a series sequence to be 1 over n, and the b sequence to be 3n. Right, now we know that 1 over n goes to 0, right, as n goes to infinity. But we also know that 3n does not converge and is not bounded. Right, so 3n grows as n grows, right? Right, so the limit here is definitely not 0 when we multiply the terms, as you can plainly imagine, right? Okay, so that is an important theorem, and we'll use this in. I don't think it'll come up in any of the proofs we do today, but this is one that we will use in future lectures, and it's just an interesting feature, right? To, you know, the fact that b sub n doesn't have to converge, but if we as long as it's bounded, then the diminishing nature of the a sequence will pull b sub n down. No matter how big those terms are, so long as they're bounded, it'll eventually get pulled down to 0. So let's take another theorem, and this is a very famous theorem which we will use today in some of the harder proofs that we'll get into in a moment. But this is the famous squeeze theorem. The famous squeeze theorem, which we will have certainly heard of. Okay, so the squeeze theorem from calculus. So if we let a sub n, b sub n, and c sub n be sequences, where there exists n naught natural number, and there exists n naught in n such that a sub n is less than or equal to b sub n is less than or equal to c sub n for all n greater than or equal to n naught. Then if a sub n goes to some limit L and c sub n also goes to L, then the result is that b sub n goes to L. Okay, right? And so this is, so the idea here is that you've got these three sequences. They may start out in whatever orientation to one another. But if these three sequences fall into this configuration, at some point as you move out into the terms, and once they fall into that configuration, they stay in that configuration, then if this guy here goes to L and this guy here goes to L, then obviously that's going to force the middle term, the middle sequence, to go to L as well. And so that's the idea of sort of squeezing the thing down. So b sub n may kind of do whatever, but as long as b sub n is between a and c, then if those two go to L, then b goes to L as well. All right, so this is the famous squeeze theorem from calculus. Okay. All right, and we're going to use the squeeze theorem in some of the coming proofs. So we're not going to prove it right now. I think a proof is presented in calculus that I think is pretty good. So you can go back and review that. So we'll use it to prove some kind of trickier results here in a moment. But the coming proofs will definitely use the squeeze theorem. But in addition to that, they'll use the binomial theorem pretty liberally as well. So I want to restate that just for people. And this is the binomial theorem, because this is something you may or may not have familiarity with. I would think you probably have, but if you haven't, let's just level set here. So for a real number and n a natural number, the following is the binomial theorem. So 1 plus a to the nth power is equal to some expansion, right? So this can be expanded, obviously. So if it's squared, you know how to do that. That's just the old FOIL method. If it's to the third power, it becomes a little more complicated, and so on, right? But whatever n happens to be, there's a pattern to the way this can be expanded, and it looks like this. So it's equal to the sum from k equals 0 up to n of n choose k. So this is the choose function here, and then times a to the k power. All right, and so let me just write some of these terms out. So this would be n choose 0 times a to the 0 plus n choose 1 times a to the 1 plus ... plus n choose, ultimately n, a to the n. Okay, so this is the binomial theorem. Now, just to recall, what do these choose functions do? So n choose k, remember, is equal to n factorial divided by whatever k factorial is times n minus k factorial. Okay, so this is the binomial theorem, and it gives you a way to express this expansion in general. Right now, key thing here is a is obviously a real number and n is a natural number. Right? N can't be 1/2 or something. It doesn't really work then. Okay. All right, so that's the binomial theorem, and we'll come back to this. We'll use this to set up some of our inequalities in the following proofs, and we'll also use the squeeze theorem as well. Okay, and so let's talk about a couple of key sequences that we'll use repeatedly as we're proving, as we're working through more complicated expressions or complicated theorems. These proofs will come back again and again. So let's state some of these, and some of these we'll have seen from calculus. I would say probably calculus 2, maybe towards the end of calculus 2, these will come up. Okay, so the first one is if p is greater than 0, then 1 over n to the p power converges to 0 as n goes to infinity. these are all as n goes to infinity. Okay. So the sequence 1 over n to the p, where p is just some positive real number. Okay, so that's one we've seen, definitely. Again, another similar, if p is greater than 0, then 1 over the nth root of p goes to 1 as n goes to infinity. Okay, so as you increase the root that you're taking in the denominator, this sequence converges to 1. Okay. The third one is that the nth root of n converges to 1 as n goes to infinity. So that's very... we'll prove this one. We'll come back to this one. It's very tricky. And we'll also prove 4. If p is greater than 1 and alpha is a real number, then this sequence, n raised to the alpha over p to the n, this converges to 0 as n goes to infinity. And we'll prove that one as well. Okay. And 5 says that if the absolute value of p is less than 1, so if p is between -1 and 1, then p raised to the nth power goes to 0. Right? We'll definitely have seen that one. That's a very familiar. So we're talking about So we're talking about 1/2 raised to the nth power, that goes to 0. 1/3 raised to the nth power goes to 0, etc. So these values between -1 and +1, so kind of like rational numbers, proper fractions between those in that area. Okay, and so then the last one that we'll state here, and again, these are all really important, and I would recommend you try to prove them, but obviously in the interest of time, I'm not going to prove them all. But the sixth one is that for all p in R, for all real numbers p raised to the nth power divided by n factorial. Well, what do you think is going to happen here? Well, we know that n factorial grows very rapidly, much faster than p to the nth power, no matter the size of p. That goes to 0 as n goes to infinity. Okay, so let's focus in on these two here, and we'll prove those two. And the remaining statements there, I'll leave to you. You can, if you could give them a try. They're probably all pretty tricky. But if you can't figure them out, you could go look for hints on the old internet. They'll be there for sure. So let's take a look at the proof of 3, right? And so remember, for 3, we're trying to show that the nth root of n converges to 1 as n goes to infinity, right? So that's what we're out to show. Okay, so this one is going to be very, a lot of the kind of moves that you would that you're going to see in this particular proof are not things you would easily think of, right? And so the fact that I introduced the squeeze theorem just a moment ago, and I reminded you of the squeeze theorem, and I reminded you of the binomial theorem, means they're going to play a key role, and we're going to start with the binomial theorem here. So we're going to let x of n equal the nth root of n minus 1. And just note here, right, note that n is equal to the nth root of n plus 1 minus 1 raised to the nth power, right? Now, obviously, plus 1 minus 1, that's just 0, and the nth root of n raised to the n is just n, right? So this is clearly true. Okay, and so if x of n is nth root of n minus 1, then notice that this is equal to just 1 plus x to the n. X sub n to the n, right? Okay. So remember, this here is the nth root of n minus 1, right? So you can see that's all equal to n. Okay. All right, so then by the binomial theorem, we're going to expand this thing and set up a very nice, we're going to set up a nice inequality. So by the binomial theorem, we have n is equal to 1 plus x to the n, x sub n to the n. That's just our choice of x of n. That's not the binomial theorem yet, but here's the binomial theorem. This is equal to k equals 0 to n of n choose k to the x of n to the k, right? So that's the expansion here that is dependent upon k, or dependent upon n. Okay, and I'm just going to expand this, write out some of these terms because it'll just help make it clear what we're doing here. But this is going to be equal to n choose 0, and again this is x to the n to the 0, plus n choose 1 times x to the n, plus n choose 2 times x to the n squared, plus dot dot dot, plus n choose n, x to the n raised to the n. Okay, now, so there's k plus 1 terms here, right? Or sorry, n plus 1 terms. Okay, and all of these terms are positive, right? And the choose terms are always positive, and x sub n is always positive, and we're raising it to some power, so it remains positive. So all of these terms are positive, and so this entire sum is certainly greater than, strictly greater than, this sum is strictly greater than, well, I'm going to actually say, okay, I'm going to say greater than or equal to. It's greater than or equal to n choose 2 x of n squared. Now notice this is just that term there. It's the third term in the sequence. So all n plus 1 terms is going to be greater than or equal to just the second term. In most cases, it would strictly be greater than. Okay, but in this case, we'll say it's greater than or equal to. And this is going to be equal to, let's write out what this term is. This is n choose 2, which is n times n minus 1 over 2 times x of n squared. Okay. Okay. All right, so we know that, all right, what did we get out of this? We know then that n is greater than or equal to n times n minus 1 over 2 times x to the n, x sub n squared. And this is going to be true for all n greater than or equal to 2. Okay. So that implies that 2 divided by n times n minus 1 times n will be greater than or equal to just x sub n squared. Right, then obviously you can cancel the 2's, and that tells us then that 2 over n minus 1 is greater than or equal to x sub n squared. Okay, and so we have what? Well, we know that x of n squared is greater than or equal to 0, right, for all n. So 0 is less than or equal to x sub n squared, which is less than or equal to 2 over n minus 1. And this is true not for all n, but for all n greater than or equal to 2. Okay. And so finally, we know that 0 is less than or equal to x sub n, which is less than or equal to the square root of 2 over n minus 1. Okay, so we've got this guy. Now what happens, so we've kind of set up a nice little squeeze theorem here. So you can think of this as the sequence, it's constant sequence is 0, so obviously the limit is 0. What's the limit up here? What's the limit up here? Well, this is one that we've seen before, right? This is the limit as n goes to infinity of basically the square root of 2 over the square root of n minus 1. We know that that equals 0. Okay, and so the squeeze theorem together with this fact tells us that, once we get out past n equals 2, this is between these two values as n grows without bound, right? So whatever the limit is up here and whatever the limit is up here, if they're the same, then x of n must have that same limit. And indeed, that's what we see. So obviously this goes to 0 and this also goes to 0. Then that means x of n approaches 0 as n goes to infinity. Okay? Right? And what was x of n, remember? Right? X of n goes to 0. That means the nth root of n minus 1 goes to 0. Okay? And so that's like saying that the limit as n goes to infinity of the nth root of n minus 1 equals 0. Right? And so the obvious implication there is that the limit as n goes to infinity of the nth root of n, right? So if this sum here goes to 0, then that means this piece must go to 1, right? And that's exactly what we were trying to show. Okay, so the limit as n goes to infinity of the nth root of n is equal to 1. Okay, and so that's the proof of part 3. Okay. All right. Let's prove part 4. Let's prove part 4. Now remember, so that one wasn't too bad. I mean, obviously some of those moves are a little tricky, but part 4, I think, is a little bit more fun even still. So let's take a look at that. So proof of 4. Okay, so remember what that is. We wish to show that if p is greater than 1 and alpha is a real number, then n to the alpha over p to the n converges to 0 as n goes to infinity, right? So that's what we were trying to show. That was the part 4 of the theorem. So let's go ahead and do this. So we're gonna let k. We're gonna introduce a number k. Okay, so we're gonna let k be a natural number, and we're gonna choose a k such that k is greater than alpha. That'll be very important towards the end. So k needs to be larger than whatever alpha is. Now remember, alpha is just a constant in R. So alpha is not changing or growing. Alpha is just a constant in R. Okay, and so we'll let k be a natural number with k greater than alpha. Then since p is greater than 1, right, by assumption, we'll write p equals 1 plus q, right, with q, obviously in this sense p is greater than 1, then q must be greater than 0, with q greater than 0. Okay, and then that means we can use the binomial theorem. So by the binomial theorem, p raised to the nth power is equal to 1 plus q to the nth power, which is equal to the sum from k equals 0 to n of n choose k, q to the k. And I'm going to write out some of these terms here again. And so these would be n choose 0 plus dot, dot, dot. And I'm going to kind of jump up here because I want the kth term in here. N choose k, q to the k, plus dot, 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 plus n choose n, q to the n. Okay. And so this is the normal expansion for this this kind of a 1 plus q to the n. Okay, now, so this is just the binomial theorem. But whenever, for a certain binomial theorem, so for certain expressions, specifically when n is greater than 2k, right? So when n, whatever k happens to be, when n is larger than twice k, we have the following. We have actually that the entirety of the sum is greater than n choose k q to the k. Now I'm going to leave that to you to look into, and I think if you just take some examples, you can see why that works. So I'll say try a few examples. But you can imagine that could be the case, right? That for certain sequences, specifically where the size of n is greater than 2k, then n choose k to the qk is less than the entirety of the sequence. And so what is this one? Let's expand that. It's going to be n times n minus 1 dot dot dot, and then remember this is n choose k, so this will go up to n minus k plus 1, all divided by k factorial times q to the k power. Okay, so we have this nice little starting point for setting up an inequality. We've got p to the n power is greater than this thing, right? So the kind of the takeaway here is that p to the nth power is greater than n times n minus 1 times dot 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 n minus k plus 1 over k factorial times q to the k power. Okay, now again, double check why this works. This is a little hand wavy at this point. Okay, so I'll rewrite that. Okay, so just so we keep this piece of it fresh in your mind, that p of n is greater than n times n minus 1 times dot 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 n minus k plus 1 over k factorial q to the k power. Okay, so this is true whenever n is greater than 2k, right? So we're obviously assuming n is greater than 2k. Okay, so n, remember, is how far out in the sequence we have to go. So n is greater than 2k. Okay. So note, if n is greater than 2k, that implies that k is less than 1/2 n, right? And so if k is less than 1/2 n, that's going to imply that n minus k is greater than 1/2 n, right? So if k is less than 1/2 of an n, then if I take n minus 1/2 of an n, then I'm going to have something larger than 1/2 of an n, right? Right, and that's going to imply that n minus k plus 1 is greater than 1/2 n plus 1, right? Okay, so again, this is all kind of like, where's this going? And I get that, but the assumption here is that n is greater than 2k, and so remember we chose k at the onset, right? So n is greater than 2k, and that means k is less than 1/2 of an n, and so that means n minus k is greater than 1/2 n, and n minus k plus 1 is greater than 1/2 n plus 1. So again, just adding 1 to both sides. And then here's where we get this nice little setup. So 1/2 of an n plus 1/2 of n plus 1 is larger than 1/2 n. Okay. And so that's what we really need from this, is that n minus k plus 1 is larger than 1/2 n, right? So long as n is greater than 2k. That's the criteria up front. Okay, and so what's the significance here? Well, if you look up above this expression here, right? So you've got n, and then you've got n minus 1, and you've got n minus 2, dot, 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 n minus k plus 1. So these, the terms in this product here, n minus 1, they start large. N is the largest, and n minus k plus 1 is the smallest. Okay, so the smallest terms in this product is still, the smallest term in this product is still larger than 1/2 n. Okay, that's the key. The smallest term in the product, n minus 1 dot 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 n minus k plus 1, is still larger than 1/2 n. Okay. All right, so then we're going to use that fact, and it's going to be very, very key to the proof, right? So what we got above is that p to the n power is greater than n times n minus 1 dot 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 n minus k plus 1 divided by k factorial times q to the k power. Right, now this is certainly larger than n times n minus 1 dot 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 times 1/2 n over k factorial times q to the k, right? Right, because this n minus k plus 1 is larger than 1/2 n. That's what we just showed. Okay, and then we could continue on like this, subsequently replacing all of these terms with 1/2 n, and that's what we're going to do. So this here is larger than 1/2 n. Obviously, n is larger than 1/2 of an n. And n minus 1 turns out to be larger than 1/2 of an n as well. And so on, all the way down the line, right? Because the terms in this product are all decreasing in size. Okay, so you get this. And the fact that these are all the same means we can clean them up a lot, right? And so this whole thing is equal to n to the k over 2 to the k times k factorial, right? So just bringing the 2's down below, there's k of them, and the n's up top, there are k of those. And so then we'll leave the qk on the end here, like so. Okay, so we have p to the nth power is greater than this. Okay, it's greater than that. All right, so what's the value of that? Well, remember what we're trying to show is that something over p to the nth power converges, right? So we're trying to show something about the reciprocal of p to the n, right? And so we're gonna, what does this imply when we take the reciprocal? Well, the reciprocal, the implication with the reciprocal would be then that 1 over p to the nth power is less than or equal to 2 to the k times k factorial over n to the k times q to the k, right? So that's the reciprocal. All right. And so we now remember n is the thing that's going to infinity, so all of these k's are just whatever, some constant that we've chosen at the onset. So now we can toss in the n to the alpha. Remember, n is going to grow also, but alpha is constant. So this implies that n to the alpha over p to the n must be less than or equal to 2 to the k power k factorial over n to the k power q to the k times n to the alpha, right? Just multiplying both sides by n to the alpha, right? And then let's rewrite this because it's not obvious what we can do with this yet. So this would be 2 to the k factorial k 2 to the k times k factorial over, and I'm going to say q to the k, right? So this is all the k pieces here. And then what do I have left? I've got n to the alpha divided by n to the k. Now, remember, k was chosen so that it's larger than alpha, and so this would be 1 over n to the k minus alpha. Okay, so just kind of combining these two pieces using the sort of normal approach there. And so recall, k was chosen so that k is greater than alpha, and that implies that k minus alpha is greater than 0. Okay. All right, and so what do we know? All right, so now we've got some nice pieces here. Let's put it all together. So we know now that 0 is less than or equal to n to the alpha over p to the n, and that is less than or equal to this piece here, 2 to the k factorial over q to the k times 1 over n raised to the k minus alpha power. And so, again, k minus alpha is greater than 0. And so by part A of the theorem, well, by part 1, theoretically speaking, maybe you should prove part 1 before you accept this. By part 1 of the theorem, 1 over n to the p goes to 0 as n goes to infinity. The assumption there is that p is greater than 0. And so that's exactly what we have here, right? Think this piece here anyways. Think of this as the p, which is greater than 0. So this part of it goes to 0, right? And obviously, constant sequence 0 goes to 0. So both ends of this go to 0, and whenever n is larger than 2k, k chosen up front, then this is between the two. Okay? And so if the two series on the outside go to 0, then the series in between goes to 0. So the implication here is that the limit as n goes to infinity of 1 over n to the alpha over p to the n. So that ratio, n to the alpha over p to the n, is equal to 0. Okay, so hopefully that's clear. That's obviously a pretty tricky inequality to set up, right? Take a fair amount of work to think that through. But I think it's definitely something that would be, when you're presented with it, you can certainly follow the reasoning there. Okay, let's just this theorem is a laundry list kind of theorem, and there'll be a lot of applications. Let's just take a look at one really quick. This is one that you've seen before, but if you consider this sequence 2 times n plus 1 over 3n plus 2, we know that the limit of this thing is 2/3, right, from Calc 1. But the way that we got there, the way that you would get to that, is through this theorem, right? We would factor an n out of the top, and you'd get 2 plus 1 over n. You factor an n out of the bottom, and you get 3 plus 2 over n. And then this, of course, is 2 plus 1 over n over 3 plus 2 over n. Now, if you consider the top and the bottom separately, right, we know basically on part 1 of the theorem that we just talked through, we know that the limit of 2 plus 1 over n as n goes to infinity is equal to just the 2, because this piece goes to 0. And the limit as n goes to infinity of 3 plus 2 over n is equal to 3. And so this goes to 2/3 as n goes to infinity. And so this is one that we'll have seen. We'll definitely have seen this kind of thing. And it just kind of falls, the point of in raising it is that it falls back on the theorem we just proved. Okay. All right, I think that's where we'll end, right? So again, just the point of the lecture was just to kind of bring some of those calculus limit theorems back into our purview and prove them a bit more rigorously. And we'll continue on in this way for a while. The next time we get together, we'll talk about monotone sequences. And so we'll look at even trickier sequences and trickier theorems from Calc 1. Until then, take care, and we'll talk to you all later.